Exercise 2135 is asking you to do some multi-step syntheses with an emphasis on forming new carbon-to-carbon bonds. And that can be a little tricky sometimes because, unlike the functional groups, the carbon bonds don't always stand out as much. So you have to sort of squint a little harder. Now what we see here is we start with a carboxylic acid in A. And so you should see the OH and sort of think of it as a leaving group. What nucleophile replaced it? Well, we see another bond. We see more carbons here. And so this bond right here seems to have been formed with a carbon nucleophile. So it is a single bond, and so that narrows down the choices we can use to cyanides, Grignards, or Gilman reagents. So cyanide, Grignard reagents, or Gilman reagents will all create a carbon-to-carbon single bond. Note that Friedel-Crafts reagents also create carbon-to-carbon single bonds, but they do it to benzene, and this bond is not attached to benzene immediately on either side. So our other options are Diels-Alder reactions, which create a ring, and Wittig reactions, which create a carbon-to-carbon double bond. So those are sort of our three things that we might keep in mind as we try to add this red nucleophile onto our molecule. Okay, well, when would you use each of these? You'd use a cyanide if you want to introduce a functional group with the carbon. But we don't see any functional groups on that carbon chain, and if anything, we kicked things off. So because we're not trying to introduce new functional groups beyond the number of functional groups that are already present in the reagent, we probably won't use the cyanide. So that brings us down to a Grignard reagent and a Gilman reagent. Now remember, you'll recognize a Grignard reagent because you'll have a magnesium bromide bonded to the carbon. Now, magnesium has very low electronegativity, and so you get this huge, almost ionic bond between the magnesium and the carbon. Gilman reagents, by contrast, you'll recognize by lithium and copper. Copper is much further to the right on the periodic table than lithium, and than magnesium is. It's much further to the right than magnesium is, and so it is more electronegative. And so the bonds that it's going to form with carbons, and it has to form two of them, the bonds that it forms with carbon is not quite as polar as the bonds that magnesium forms. Sure, it's still a metal, it still loses electron density to those carbons, but it's not as polar, it's not as close to being an ionic bond as Grignard reagents are. So Grignard reagents are strong carbon nucleophiles, and they'll react not just with carboxylic acids and their derivatives, but also with aldehydes and ketones. Gilman reagents, by contrast, are weak carbon nucleophiles. They will only react with a strong electrophile, such as you find on carboxylic acid derivatives. Well, what do we want here? If we try to react either of these with this original molecule, we have a problem because the H here on this carboxylic acid is acidic. And so these nucleophiles can act as bases and just steal the hydrogen rather than attack the electrophile. So we have to replace this with something that is not acidic and hopefully also more reactive, because that would improve the efficiency of the reaction. So we sort of have a trick up our sleeves. You can always turn a carboxylic acid into the most reactive and not at all acidic derivative, and that is an acid chloride. So there's only one way to turn a carboxylic acid into an acid chloride. That's by treating the carboxylic acid with thionyl chloride, SOCl2. So now we don't have to worry about that pesky hydrogen. We know that our nucleophile will attack the carbonyl carbon, which is an awesome electrophile in an acid halide. But which one do we want to use? The Grignard reagent or the Gilman reagent? The strong carbon nucleophile or the weak carbon nucleophile? If we treated this with a Grignard, after the first addition, the carbon nucleophile would attack once, and you would have the carbon attached there, replacing the chlorine. But because it's strong, it would attack again, and you'd have a second equivalent of the carbon chain. And that is not quite what we see here. We only see one new bond to a carbon. We don't see two. In other words, we want to form the ketone. Now, you may say, wait a second, you don't have a ketone in the product. We'll deal with that. But we only want one equivalent of the carbon chain to add. And therefore, we do not add a Grignard reagent. We will not add this Grignard reagent. We only want to add one equivalent of the R group, so we'll use the weaker carbon nucleophile, the Gilman reagent. Now, the Gilman reagent we want to use, whenever you think about what it would look like, you just draw a copper and a lithium together, and then whatever carbon chain you want to add, and here we have two carbons on that chain, draw that attaching to the copper. So there's one ethyl group, and there's another one. So that's our dialkyl lithium cuprate, as it's sometimes called, or our Gilman reagent. So here, these carbons are bonded to the metal, so they're more electronegative than that. They have a slight negative charge and can act as a nucleophile. So one of them takes its electrons and attacks the carbonyl. This goes up. You end up with a tetrahedral intermediate that then snaps back down, and ultimately you have a nucleophilic acyl substitution where this ethyl group, and notice it is an ethyl group, 2 carbons there, 2 carbons. That ethyl group has replaced your leaving group, the Cl. And that only adds once, because this is a weak nucleophile, so it will not add to an aldehyde or a ketone, which is what we have here, a ketone. Okay, well, we're closer to what we want. We've added the carbon, but we do notice one other feature, one other difference here. As we look at the molecule we have and the molecule we want, you notice that the molecule we have has 2 bonds to an oxygen, the molecule we want has only 1. And so we can reduce that. We can treat that with a strong reducing agent, like lithium aluminum hydride, and then just stabilize the charges that form afterwards by adding water, doing proton transfers. So what that'll do is it will replace the pi bond here with a bond to a hydrogen, and then the oxygen will go up, and it'll gain a hydrogen from water. And the hydrogen on the bottom won't be drawn in because it's implied in the skeletal structure, and you can see how that gives us the product we want. So this recipe that we saw had sort of 3 or 4 steps if you count the water as a separate one. First, we used thionyl chloride to turn the carboxylic acid into the less acidic and more reactive acid chloride. Once we had that, we treated it with a weak carbon nucleophile because we only wanted 1 carbon chain to add. And in this case, it was a Gilman reagent, so it had copper and lithium and 2 ethyl groups coming off. Now, one other way you might see that is like ET2. It's 2 ethyl groups coming off of there. So once we did that Gilman reagent, we added that. We can add the second nucleophile because we wanted to reduce this, get rid of the 2 bonds to oxygen, turn it into just 1. So reduce it with a reducing agent like lithium aluminum hydride, and we could follow that up, stabilize all those charges there with the water. So that's one possible recipe for how you could accomplish that change. Now, if you notice, you can think about these 2 steps using a carbon nucleophile and a hydrogen nucleophile, and you didn't necessarily have to do them in that order. You could have added a hydrogen nucleophile first. So if you already had, so imagine you have the carboxylic acid. You could do the thionyl chloride to turn that into an acid chloride. And you could add a hydrogen first. But just like you used the weak carbon nucleophile, you would want to use a weak hydrogen nucleophile because you only want to add 1 equivalent. The weak hydrogen nucleophile that we've seen is lithium aluminum trialkoxy hydride. We've discussed that in previous videos. That would add just one equivalent of a hydrogen. It would react with an awesome electrophile, a truly stellar electrophile like an acid chloride, but it would not react with the aldehyde that you form after that one hydrogen replaces the chlorine there. And once you have that, you could use any type of Grignard reagent you want, because you only can add something one more time here. So you could, or any type of carbon nucleophile that you want. So you could add a Grignard reagent. You could have an ethyl magnesium bromide, and then follow that up with water, just like with after lithium aluminum hydride. That will stabilize the charges. So you have that ethyl group, the hydrogen is still there, and now you have OH here. But the hydrogen is implied. Notice that gives you the same answer. Now I know I went through that very quickly, but I just wanted to show you an alternative way of thinking through this same thing so that you can see multiple perspectives. We used a weak electrophile first because we only wanted one equivalent to add. The weak carbon nucleophile was the Gilman reagent. The weak hydrogen nucleophile is the lithium aluminum trialkoxy hydride. And after that, we could use any type of nucleophile we want. So if we use the weak carbon nucleophile, we can use a strong hydrogen nucleophile afterwards, because there's only enough space to add one more thing. If we use the weak hydrogen nucleophile, then we could use a strong nucleophile afterwards. It doesn't matter which one. And either way, you'll end up with the same product there. Okay, so much for A. How about B? Now with B, you would look at the reagent and you'd see a bromine, so you'd think, okay, leaving group, and maybe another association you'd have with that is a Grignard reagent. Maybe we could add magnesium in here, and the magnesium would insert itself in between the benzene carbon and the bromine and create a sort of almost ionic bond, really polar bond with a lone pair here. Oops. So that's one possibility. I have no idea where to go from there, but just looking at that, seeing the bromine, knowing bromine is a good leaving group, and you can also make carbon nucleophiles with bromine by making a Grignard reagent, that's something that comes to mind. Sort of brainstorming rough draft. Who knows, maybe that won't be useful at all. Then I get stuck. I look at the product, and here I have a carboxylic acid derivative. Now, carbon double bonded to oxygen, single bonded to an ether, that's an ester. And I can think of this as a sort of nucleophile that came in. It came in, and since I'm just dreaming here, why not have it react with an awesome leaving group, an awesome electrophile in acid chloride? You can picture this acid chloride, the chlorine being the leaving group, and this red thing coming in as the nucleophile. Well, how could we create that nucleophile? We have the ring already, but if you compare the ring that we have with what we have here, you'll see there is a new carbon-to-carbon bond. Now, normally, you'd see a carbon-to-carbon bond to a benzene ring, and you'd think, the way I'm going to form that is a Friedel-Crafts reaction, but we already have the bromine there. Friedel-Crafts would be the most useful if you had started with just pure benzene, nothing is on it. But here we already have the bromine, so we might as well make use of it by making this Grignard reagent, and we can have it react with the carbon in several ways. One way is to have it react with carbon dioxide. If you react that with carbon dioxide, then it could attack this this electrophilic carbon. This could break open, and you could have a sort of carboxylate, a carboxylic acid with a negative charge. And if you follow that up with hydronium, then you end up with the carboxylic acid, benzoic acid. Well, we've added the carbon. We definitely have an oxygen here, but it's too much. We just need one bond to an oxygen. Here we have three, so we could do a reducing agent. We could use something like lithium aluminum hydride, followed by water. That would give us that alcohol. So these are separate steps. Now once we have that alcohol, we could just treat it with our acid chloride, and we do the nucleophilic acyl substitution. Now you'd want to add a little bit of pyridine in there as the base to steal that hydrogen off after it does the nucleophilic acyl substitution, but what you'd end up with is your product. The product that we wanted up there. And that's a little long, a little lengthy, but I wanted to show you that one because it involves a reaction that we have used before. We've done this, we've added this carbon there by adding carbon dioxide before. Another possibility, instead of using carbon dioxide here, is you could sort of shorten the process a little bit by treating this with an aldehyde, formaldehyde specifically, an aldehyde with just one carbon. Now, I know that doesn't seem very obvious at first. It requires you to recall a little bit from the previous chapter on aldehydes, but that can attack that, burst the pi bond open, and in that case, we really just have that there. And so we can treat that with water or acid, and that would give us our alcohol, and notice that this next step becomes unnecessary. So that's kind of nice. Simplification there. So you just want to treat that with the acid chloride and pyridine, and you'd get that done. So that's sort of a shorter version of itself. Either way, though, would work. Either way, you would get the product, it would be an acceptable answer. So here in this shorter version, we dumped some solid magnesium into our solution. We followed it up with a 1-carbon nucleophile with just 1 oxygen on it. Formaldehyde was a good formaldehyde, the smallest possible aldehyde, was a good option for that. We did the protonation with some hydronium, and then we just treated it with the acid halide, or the acid chloride here, adding a little bit of pyridine. That's that nitrogen, almost benzene-like thing. The lone pair there can act as a base to remove the hydrogen in the alcohol. And that would give us your product. That would give you the product. So we sort of saw 2 ways to make that happen. Hopefully seeing those 2 ways sort of gave you a little bit more perspective on how you can make that reaction happen. All right, let's look at C. Now we see a similar thing here, except we don't have to use a Grignard reagent. This starting material is very similar to this part of the molecule here. And we need to get rid of the nitrogen. And a convenient way to get rid of that nitrogen, an easy way, is just to mix it up, swish it up with some acid, some hydronium. That hydrolyzes the nitrile, and we saw the mechanism for that in the video on the reactions of nitriles, and that turns that into a carboxylic acid. Now, when we look at this and we compare this with, because another thing we'll notice is in this product, you sort of have a carboxylic acid derivative there. You have an ester, carbon double bonded oxygen, with an ether on one side. And so you can sort of think of that ring as your nucleophile. So if we can create that, then we can treat it with an acid chloride, ethanoyl chloride, and we would get our product. So how can we turn what we have into this red group there? The first thing you'll notice is that here we only have 1 carbon, and in this group we have 1, 2, 3 on that branch. Moreover, the carbons that we add have just 1 carbon in them. They're the same type of branch. So we could treat this with a Grignard reagent, a strong carbon nucleophile and more than one equivalent would add. And we can't react a Grignard reagent, and you look at the branch and that tells you what kind of carbon chain you'd want on the Grignard reagent, so a methyl group. We can't react the Grignard reagent with the carboxylic acid because the carbon nucleophile, that negative carbon, could just steal the positive hydrogen there and become methane, and because that's acidic. So that would be counterproductive. So we can get rid of that acidic hydrogen and turn this into a more reactive and efficient molecule if we treat it with thionyl chloride. We'll turn it into the most efficient of the most reactive of the carboxylic acid derivatives. So now we don't have that hydrogen there anymore to worry about, and this is really reactive, so it's going to react very efficiently. So we can treat this with our Grignard reagent, and if we treat it with excess, then two equivalents of this will add. The first equivalent will replace the chlorine. It's a nucleophilic acyl substitution. So you'll have just that one of the methyl groups. But you still have an electrophilic carbon there, and another equivalent of the Grignard reagent would add and create another bond to the methyl group and a negative oxygen. So you just want to follow that up, as with any strong, any Grignard, any carbon nucleophile, well, Grignard reagent or Gilman reagent, with water. And that will do a proton transfer to stabilize that negative charge. So it turns into an OH. And now you'll notice that we've made that group that we have above there. Okay, so once we have that, we just need to react it with our acid halide. And that gives us the two methyl groups, the oxygen. The oxygen replaces the chlorine, so you have the acetyl group there. And just don't forget to add a little pyridine, the base. That's going to steal this hydrogen away so that it's not giving a positive charge to that oxygen anymore. And that is your product there. So overall in this process, we hydrolyzed the nitrile by using H3O+. That turned it into a carboxylic acid. Then we turned the carboxylic acid into the less acidic and more reactive acid chloride. There's only one way to create an acid chloride, and that's by combining thionyl chloride with carboxylic acid. Once we had that, we wanted two equivalents of a methyl group to attack. So we used excess methyl magnesium bromide. That put two carbon branches there. To stabilize the charges that developed, after that we just added some water so we can do some proton transfers. And that left us with this alcohol, which is able to do a nucleophilic acyl substitution reaction with a small acid chloride. Just don't forget the pyridine to help with the proton transfer off of the alcohol to stabilize the charges, and that is the overall final recipe that you need. Mix that in a boiling cauldron and your witch's brew would produce this magical transformation. So in this video, we have seen some multi-step syntheses that involve carbon nucleophiles, and you can see how it is almost a category unto itself. It still follows all the same principles, but it's just a little harder to see sometimes because the carbons don't stand out as much as other functional groups do. So watch out for them, and these are the reagents that you would want to use.